So where are you going to record separately?
यहाँ पे कर पाँच इसमें शुरू कर देते हैं इसमें वो रिकॉर्ड आप एंड करेंगे ना वो एनकोड करके यहीं पे रहेगा देन विल चेक दोनों कंपेयर करके चेक कर
Yeah, you can start whatever you want. This is already on.
हाँ ऑन लाइव स्ट्रीम हो गई
हाँ
सिर्फ इसको जूम में ना यहाँ पे देखो आप जब स्टार्ट करेंगे
this computer.
Yeah.
Thank you. All right, questions? No questions, but bad news. No questions is bad news. Either you haven't gone back home and looked at it, or interesting things are not happening. No questions. All right, just to recap, what are we talking about? Convex functions. So as time progresses, this is the easiest way to remember a convex function. Specific definition is that x belongs to chi, that's the domain, is convex, and f of lambda x plus lambda y, which is much easier to remember this way. Let's say this is y, this is the function. So this is the valuation of f of lambda x plus or minus lambda y. And that lies below or above? Below. Trust me, it's not always easy to remember the direction of the inequality. It's much easier to always have this picture in mind. Okay. So why am I harping on the fact that this better be convex? I've been insisting again and again that the domain of f better be convex. Why? For all xy to x down. What will go wrong if the domain is not convex? Let's say I'll give you that. Let's suppose that is true. Now what will go wrong? For certain specific x and y's, it could be possible. Right? You're right that in general, this function may not, like this lambda x plus 1 minus lambda y need not belong to x. There's something more going on. Okay, let's maybe delay this a little bit. We'll come to that why it is important to have that. Okay, so let's look at examples of convex functions. We saw one constant 2 x f of x equal to x, which is both convex and concave. You can put x square, x power 4, and so they all belong to the same class. Now, what other new functions do we know which are also convex? Sorry, e to the power x. Yes. Right. Can you actually show that this is convex from first principles? Just by the definition. And do you need to care about where x lies? All of R is fine. Does something need to be checked for x less than 0? Or we don't have to worry about it? Okay. So how do you prove that e power x is convex without appealing to the derivative tests and so on and so forth?
We don't define slope yet, but we can see the slope is also included. That's it.
See, for that we have to prove that this is differentiable. And so I'm not asking you to do it. Can you do it is the question. Are these characterizations avoidable is the question. We'll do that anyway. That if it is derivative exists, what happens? If second derivative exists, what happens, and so on. Those are exactly required to simplify our life. Is there any other simple fact which implies that it's convex? Okay, you'll have to establish that. It's okay. Suppose that is true. Then what do you do? Is that sufficient? Supposing, are you trying to claim that if suppose another g of x is there, which is always greater than f of x, and f of x is convex, is g of x convex? Are you hinting at that? Is it actually true? Oh, counter example. Is it clear what we're asking? Suppose f of x is convex, and I give you g of x is always greater than or equal to f of x. Does it mean that g of x is also convex? You can create all sorts of shapes. Right? There's nothing stopping you. So why would e power x greater than x help? That alone should not help. There's something else should also matter. I'm just trying to impress upon you that it's not always easy to check if function is convex or not. And that is why we'll do what we will do. Alternate characterizations of other things in life which help us to prove or disprove that the function is convex or not. Okay, other functions which are not this type. Pretty sure you've seen more convex functions. Let's wait for that.
Negative of natural log.
Negative, sorry?
Natural log.
Natural log is convex. See, when I say convex, I don't differentiate between convex and concave. You give me a concave function, I'll happily write that. No problem. Because if all the lines flip, so it doesn't really matter. So if you give me a concave function, I can always produce a convex function. Yes, so logarithm is a concave function. Something non-trivial, like it's not obvious that it is convex. or you don't know just by memory that it is convex, but you think it is convex.
K by x where k is a constant.
Sorry, k
By x. K divided by x.
by k 1 by x.
Or any constant it will be 1 by x.
Okay, is 1 by x convex?
If only one of the constants.
Okay, x greater than 0, which is fine, right? By our definition, even if I restrict my domain to be x greater than 0, it's a convex set. Okay, is 1 by x convex? And why is it convex? So compared to e to the minus x, how does one by x look like?
It's a
Sorry,
hypertable.
no, compared to e to the minus x. Can you compare e to the minus x with 1 by x?
The power x is increasing.
No, e to the minus x also goes like this. 1 by x also goes like this. Is there a way to
Minus.
Is there a way to compare the two functions?
One by e power x and 1 by x. So e power x is always greater than x. So 1 by e power x is always going to be less than.
No, that much is fine. Is there something more we can say? They're actually interesting functions. What about 1 by x square? Is that convex? We haven't yet established that 1 by x is convex, but let's take it at the face value for the time being. How would you actually try and show that 1 by x is convex? What inequality do you really want to show? All I have is this definition and nothing else. So what do I need to show? 1 over lambda x minus lambda y is less than equal to lambda by x plus, looks nasty, right? Any guess how do you do that? So you'll essentially end up getting xy less than equal to lambda x plus 1 minus lambda y whole square. Reminds you of something? If lambda is half, what does it remind you of? Some inequality you know, just AMGM. So at least for lambda equal to 1/2, this is true. Is it true for all lambdas? Are you following what I'm saying? This will essentially imply that xy is less than equal to lambda x plus 1 minus lambda y, the whole square. So if I take lambda equal to half, it exactly is the MGM inequality. But is this true for every lambda? What happens at the extreme? Lambda equal to 0 or 1?
You just get xy less than or equal to, for example, y square.
Something is wrong here.
And that's not clear.
It's not the other way around. The numerator here will not be the same as the denominator there. We cross terms. So always keep me honest.
Yeah, so it will be lambda.
Yeah. So it is lambda y plus 1 minus lambda x. So I think already it's unwieldy to do anything of this sort. So what about 1 by, so suppose if f is convex, what about 1 by f of x?
We'll have to change the domain.
For example, x square. Is 1 by x square convex? Not easy to check unless we do something. Okay, so let's just keep producing examples and we'll come to the characterization and let us resolve all of these. Any other interesting examples of convex functions? There are many, plenty. What about a norm?
This is not wrong.
Sorry?
1 by f of x is not necessarily convex.
Okay. You have a counterexample already?
E to the x square. If f of x is e to the x square, e to the x square is convex, but e to the minus x square is a paradox.
Yeah, so that in fact is true. So in general, you can't do this. So essentially, you need something, some properties of f under which this will be true. Okay, what about the norm? Is norm a convex function always?
So that would be from the triangle.
Okay, good. So let's just think of the two norm, for example. Let's just take R2 and f is nothing but distance from the origin. Is that what you want to find? Okay. Here's the distance of 0, x. And why is it convex? Is it not one line? You need one more line. So how do I check? I should check f of lambda x plus 1 minus lambda y. What should I do next?
So that will be equal to d of 0 comma lambda x plus 1 minus lambda y.
Yeah,
And that can be broken down as d 0 comma lambda x plus
because of,
triangular inequality.
yeah, so I can essentially do this f of lambda x plus f of 1 minus lambda y.
But to really define f is in such a way that lambda can be taken.
Norm is scale invariant essentially, right? So this is lambda of f of x plus 1 minus lambda f of y. Is this true? Is this okay for everybody? Why I can do this? So now do I have to restrict to two norm or can I take f to be any norm on Rn? What is the definition of a norm? Is everybody comfortable with that? Norm is something that satisfies triangle inequality. Let's put it that way. And once I have the triangle inequality, this is automatically. So all norms on Rn are actually convex. It's a very blanket statement. Okay, what else? Wow, that would be interesting. Think about it. Determinant doesn't do anything. That's the problem. So if you add two matrices, you can clearly produce. Just construct a counter example to show it's not convex. If you add two matrices, you can produce a non-zero determinant, while the components themselves, or the two matrices you're adding, have determinant 0. That's easy to construct. So that will never work. So determinant is not, but so let's suppose I give you a matrix. What function of a matrix you think is convex?
Trace will be very.
Trace is linear. So yeah, linearity will just tell you directly what is going on. Because trace of two matrices is just summation of the diagonal entries. So that would be, yes, anything more interesting, like determinant, which is not obviously linear. Something to do with eigenvalues. What about the maximum eigenvalue? So for a matrix A, let the function be the maximum eigenvalue of A. And avoid all the corner cases. What do you think is going to happen? Determinant is not. So product doesn't work. But that doesn't mean that the maximum guy doesn't work. If you know an alternate characterization of a maximum eigenvalue, it's trivial. What is the maximum eigenvalue of a matrix? Is equivalent to some optimization problem. Have you seen that? Then it's painful. So let me write it. So a non-trivial example. Let A be a. I'm just doing it for the heck of it. You can do this over more general symmetric matrix. Then f of A be the lambda max of A. You've seen something like this? You know this, that the maximum eigenvalue of A is nothing but this optimization. So take A, you pre-multiply X, post-multiply X, maximize over all possible X. Now, I've given you this fact. Now, can you claim that this function is convex? Has everybody seen this? If not, it's okay. It's not a trivial fact. You'll find it in graduate text on linear algebra most of the time. But now, given that I've given you this fact, you should be able to show that that is convex now. It's one line, essentially.
We can just expand the sum.
Sum, where is the sum anymore?
We take A to.
This is some fixed quantity, right? For each X.
Right. So
But what is this over?
it's all.
Max over something.
Over all x is that the norm just.
Yeah, but what kind of function is this? This is linear in A. And what are you doing? You're looking at max over lots of them. So max of convex functions is, that is all you need to prove this. Once you have this characterization, is nothing but max over lots of convex functions. So it's convex. So this is a non-trivial example. Maximum eigenvalue happens to be convex. Determinant is not traces. What about minimum? You know the similar characterization for minimum eigenvalue? It's not minimum of this, because otherwise all eigenvalues will be zero, like the minimum eigenvalues for each matrix will be zero. If I just simply move max to min, that shouldn't be correct. But something goes on. If you're not seen, it's okay. You essentially remove the eigenspaces belonging to the max, the second best, the third best, and so on. And in the remaining, you do this maximization. So if you want the second best, max minus 1, you essentially remove the direction in which the max exists. And you do the same maximization. You'll soon see. These are like series of Rayleigh theorems. So min won't be. Equal to 1, it will still work. I just throw in more. It won't matter because max over a larger space can only be larger, but there is nothing to be going outside of that. And you know what solves for this? What is optimizing X's? I've given you A as symmetric. So you know what X is, the optimal X? If not, forget it. This is not a. That's all. If you start thinking about the eigenvalue decomposition of A, everything becomes easy. So if you establish that for a symmetric matrix, I can do eigenvalue decomposition, then all of these are easy. That requires a little bit of work. Okay, and more non-trivial examples. Let's think of something interesting. Let's say you're an Rn, and for a point X, I just write Xn and f of X be maximum of Xi. It's a weird function then. What will it look like in 2 dimensions? Suppose I pick, this is 1, 2. So this is 1 comma. It's just going to pick value 2. That's what it looks like. What about 2 comma 2? It's going to remain Just sketching, like I'm trying to see how this looks like. Okay, now as I progress, what happens? It goes to 3. Right? I'm just trying to plot it and think of this as coming out 2, 2, 3, and so on. The 2D plane. Do you think it is convex? Weird function. On all components, you are picking the one which is the largest.
This is also a norm, right?
See, infinity norm doesn't belong to that class. It is a special norm. So let's do it separately.
And even then, we need an absolute value, just max.
Here it is just max. Yeah, so here it's not necessarily non-negative. Here it could be negative. It's a very difficult function to visualize. How does it even look like?
Yeah, it is maximum over functions.
Okay. Over what function?
F of x is
X itself.
x.
So that's one way to claim it. But even from the first principle, it's not very hard. So let you do it later. So either you can appeal to the max of functions, which I have proved here, will prove today. The max of convex functions is convex. So what is this max over? It's just identity function, which by definition are convex. But even a direct application is fine. You can just directly plant and try to check our condition. Okay, what more? What I'm trying to impress upon you, that there is like this wide variety of functions which are convex. And that's why it's important to study this course. So one nuance I want to bring out is the following, that is very important. That a function could define, so might be convex in subset of dimensions. So this is not a very precise statement I'm making. Well, hopefully, but not. The full domain. Really call it domain. Can you give an example where a function is convex in certain coordinates, but not in all coordinates simultaneously? So take R2, simple as that. Take a function which is for any point, define that point to be x comma y. So if it's a mapping from xy to something, is there a function which is, if you fix a y, it's convex in x. If you fix a x, it's convex in y, but simultaneously it's not convex in x and y together. It's called jointly convex. All our definitions so far have been jointly convex. We are not specialized to some subsets of subset of a domain. We said take any point in the domain, take another point in the domain, take the linear combination, evaluate f on that, and that better be less than equal. So that's the way we have defined it, is jointly convex. So now give me an example where it is in each dimension it is convex, but not jointly convex. Question is clear to everybody? Just think of R2. You don't even have to go beyond R2. It's not some pathological.
X square minus y square.
Okay. Why is it convex in both?
It's convex in X square.
But it's not convex in Y square. What about X times Y? What happens to that function? It's clearly convex in X and Y separately. Is it jointly convex? No? Why not? We don't like the function. Is it easy to give a counterexample? Or any argument for that respect? What does it look like? See, visualize. X times Y.
Specific name for that type of curve. I can't remember it. I like to it as the Pringle strip.
Pringles. Okay, that's fine. Saddle, you're looking for a saddle.
Yeah, saddle.
So one direction, this looks like convex. Another direction, what does it look like? Saddle. All of you remember what saddle looks like? Is that how the function looks like? Let me try to draw. Let's see if I am successful. Like this? Not a good idea, right? Okay, let's just believe that this is saddle. So this way it is like this, and this way it is like this. That's what you sit. This is the part where you sit on top. Oh, is it actually true? This is xy. Is this function x of a point x comma y is equal to x times y? Is this the correct visualization of this function? This is clear, right? As it goes away, at least in this direction, it's going higher and higher. That is clear. Why is this curving like this here? At this point, what should it be? Negative. At this point, what it should be? And at this point, what it should be? I don't know. So it has better be that at least definitely continuous. So it better should increase and then decrease because it has to cross 0. And this direction definitely it's increasing. Now this is not jointly. In a jointly convex function, what it would look like? It look like something like this. Like a cup. That's what it looks like when it's a jointly convex function. So this is a simple example which illustrates that to fix x, you start going along a particular line. They're convex both ways. Jointly, there is a problem. So you should always remember what convexity are you looking for. Everything wherever we are going to define, it's all joint convexity. Okay, any more function? This is an interesting function, which is not convex, but appears highly convex. What would happen to x squared times y squared? Would we get into such trouble?
So that will be positive. It's like,
It's the same thing from whichever direction you look, it will look like a cup rather than a saddle. So x squared times y squared will fix it. X dot y has this problem. Any other example of this type where individually it is convex, but jointly it is not? What about x by y? Individually it is still convex. You told me that 1 by x is convex. So 1 by y, similarly 1 by y is. So if we can fix an x and make sure that y greater than 0, then both x and 1 by y are convex. What about x by y? Pair function, right? Directly in same spirit. And we don't have to appeal to Hessian, like we'll all come to that. These things are easy to see.
so when you have negative 0, if x equal to 0, you will have it to take value.
Okay.
As
But
you-
now y is frozen to be greater than 0.
Y is closer to 0.
Yeah.
Okay.
Because otherwise, how do I even, it will complicate matters. So let's say y is, so the denominator is greater than 0. See, I have to remove that. Otherwise, okay, tell me, if I don't remove y equal to 0, what is going wrong? Something is going wrong.
We go to y equal to 0. But then you can't divide by the. Right?
No, so it's no longer something, right? If I allow y equal to 0 and y less than 0, it's no longer convex. That's the problem. So to make sure I don't get into that trouble, I definitely have to avoid all those things. So the function is x by y where y is greater than 0. So you restrict your domain to be that. That is perfectly fine. The domain is x belongs to R and y belongs to y greater than 0, which is still convex. What happens to the point x equal to y? So it evaluates to 1 wherever x is equal to y. So that is clear, just 1. Now we have to look around. You want it to go up, but what will actually happen? All sorts of things will happen. So if you move from x equal to y in a direction where y increases more than x, what happens? The function actually decreases. While if x increases more than y, it increases. Is not sufficient.
That's not convex.
Yeah, we want to show that it's not convex, but why is the question?
So at this rate that x equal to y, we have it as y.
Yes.
If x increases more than y, then it's increasing around 9. But the only way to be also convex is if it increases when y is increasing.
This has to be more precise because the function x squared by y is convex. That's the funny thing. So let me just pull it out today and you can check for yourself. So x by y, where y greater than 0 is not convex, while x squared by y, again y greater than 0, is convex. Surprising, right? Not really. Okay, so let me now define something with respect to a convex function. See, these things don't require the functions to be differentiable. That's why I'm doing this before talking about when the function is differentiable, what happens. Because there are equivalent characterizations of convex functions, even when they are not differentiable. So this is defined for any function. And we'll say if it's convex, then what happens? So the alpha sub-level set of a function f is defined as of alpha x belongs to the domain of f such that the picture, my pictures are always going to be this type, and this is my, so I'm drawing everything in single variable, just easy to visualize. Otherwise, I have to take a plane and all. So f of x is equal to x plus something, x minus theta whole square, or some theta. That's what this function looks like. This is my theta. And let's say this is my alpha. What is my alpha sublevel set for this function? So this is just simply this is C of alpha. Okay. Now, any observations to make from here? This is defined for any function. I just drew for one particular function what it looked like. I've not said anything about convex, not convex, nothing. This is defined for any function. Well defined, there is no problem with that. You take any function, you draw a line of alpha, just look at what it projects to. Essentially, that's what is going on. So, any observations to be made? Just the definition. Okay.
If this convex sense here, how will you call it?
Okay, is that trivial? We're saying, suppose the function f is given to be convex. Then it has to be that the sublevel set or alpha sublevel set for any alpha better be convex. Okay, why should that be true?
Because then, let's say that f was convex. So then, let's say that x comma y belong to C alpha. So then you would have that f of lambda x plus 1 minus lambda y. would be less than.
Also less than. It's just a linear combination, right? So if at one particular point the function is less than alpha, other particular point it's less than alpha. So lambda alpha plus 1 minus lambda alpha better be less than alpha because lambda is less than 1. So it's I'll write it down. I'm just saying in words. So one expects that if the function is convex, the alpha level subset will be convex. What about the converse?
So if C alpha is from.
If for a function f, C alpha is convex for every alpha. Is the function convex is the question. If it was, then it will be an equivalent characterization. A convex function, if and only if alpha sublevel sets are convex. So, everybody agrees? He's saying yes, that if every alpha sublevel set of a function is convex, then the function should be convex.
There can be a W function
Uh-huh.
where we can take that alpha to be higher than. Or.
Let's look at the W. Does it work? Okay, so now what is the alpha sublevel set?
That will not be convex.
Okay, yeah.
But if we choose it little.
No, but for every alpha, right?
For every.
Otherwise, you can always produce some weird things. So the claim is that for a function f, if alpha sublevel sets for all alpha are convex, is the function convex. In this, think of a concave function. Can a concave function have all its alpha sublevel sets convex? Because if such a thing exists, then this claim is not true.
Graphically, we can, which is non-convex, but it's alpha sublevel sets.
Perfectly fine, give me. What do you want to make? Want. Okay. Now, what do you want me to do?
The alpha sublevels will be convex, but this function is not convex.
Okay, so what are the alpha level subsets? So draw any alpha. What will happen? Essentially for this part, this much, you keep going, it'll just keep increasing. Now, what happens? This is clearly true, right? But this function is not convex because this is lying below. So that fact is, so there are many functions, this is one of them. And pictorial proofs or counterexamples are all fine. Because you can always say, you can construct such a function. There's not much difficulty. So even when you're writing a homework and you give me something like this, I'll be happy as long as the function is clearly defined. You don't have to give me values. If you're working with a counterexample and you give me something like this with a clear explanation of what is going on, that's okay. You don't necessarily have to write down what is f of x for each value of x. That might become ugly very soon. Okay. So that's not necessarily true. So the second definition is even more important. What is called as an epigraph. So that is sub-level sets. This is epigraph. So we looked at so sub-level set is a subset of the domain itself. Here we are going to increase the dimension. Okay. So let's first call the graph of a function, which will tell us what we are trying to do. What have I done? I've appended the value. So increasing the dimension of the domain essentially, going from Rn to Rn plus 1. X comma f of x is what I start looking at. This is one dimension quantity, this is n dimensional quantity. This will be a subset. So epigraph is a subset of a graph. Defined as epi of f is equal to x comma f of x such that, or rather let's write it as e such that f of x is less than equal. But for intentionally moving from f of x to t, because I need a definition here. Again, a picture. So this is my f, this is my domain. Or what is epi of f? Now it doesn't depend on any alpha. It's defined just with respect to f. Look at this definition.
What is the area above the
Not above. It's like this. So these are the t's which are allowed. T greater than f of x. That's what I'm appending to the x itself. So now it's a two-dimensional region. My domain here was one dimension. Now I've gone to two-dimensional region. That's what I'm essentially trying to do. This is your epigraph. Okay. Any observations to make similar to alpha level subsets or alpha level sets? Is the definition like you should absorb the definition for a moment. If you're not seen it, it's a non-trivial definition. That's very important on top. So epi, I think in Latin means above. It would have been easier to say above graph also. If you observe, then you can try to make an observation. What do you think should happen given that we've been talking about convex functions? For this particular choice of function, it looks nice and convex. So can you want to hazard a guess about epigraph being convex versus function being convex? We already saw we were not successful when we talked about the sublevel sets. We are not able to characterize a function and its alpha sublevel set as being equal to each other. Question is there better hope here? So which direction do you think is easy, if at all? If function is convex, is epigraph convex?
Yes, convex, yeah.
Is convex. Okay. Why?
Again, we can just take take 2 points x1 t1,
Mhm.
x t1 by t2
Mhm.
in between, and then we can so lambda of x t1 plus 1 minus lambda by t2.
Just by saying just elementary calculation. Okay, fine. We'll do this. What about the reverse direction? If the epi now reverse is if the epi is convex, then is the function convex. So the epigraph of a function is, let's say, a circle or a disk. What kind of function is f? Is it even possible?
That won't be a function.
Which one? So you're saying for a function,
Epigraph is-
sorry?
If the epigraph is a circle,
Yes.
that won't be a function.
Why?
That is not is unbounded.
Should be a- Epigraph cannot be.
If it's the x, then t is anything above unbounded, so it's unbounded.
Good. So you're at least following what a definition means. So now think about if the epigraph is convex, why should the function be convex? Is there any reason to believe that it should be convex? What is geometry? Just for this picture, what does geometry tell you? If epigraph is in fact convex, what does it imply on the function?
The function is just the boundary of.
Okay. That's correct.
So then, any 2 points that connect the boundary
Mhm.
that should lie above the.
Why? That's what we want to prove.
Right, so it should lie within the
It is convex then.
Fine.
but the epigraph itself lies above a function.
Yes.
So then the line connecting two points in the boundary must have.
Something like that. The whole point is to notice what exactly is this epigraph is. Okay, so we'll prove this formally next time. I think you more or less got it. What he's saying is look at the boundary, right? And now connect 2 points on the boundary. What do you want to show? That the evaluation of this point here should be smaller than lambda times this plus lambda times that. But why should that happen? Because this point belongs to the epi on account of it being convex. And now, by definition, T better be above all the x's. So if you hopefully you come down like this, this point should have a larger valuation than this point. That's by and large what the proof is. Now suppose this is actually true that if and only if a function is convex, if and only if its epigraph is convex. Can you use this to prove that max of f1 of f2, that's why I wanted to do this, is convex if f1 and f2 now you can for the moment assume that we have proved it. Does it directly imply this? So what is the epigraph of max of f1 f2?
Intersection.
An intersection of convex sets is convex. So that one line. Otherwise, you have to open it up and do blah, 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 blah. So once you have this machinery that what is convex, so this is a purely, this function is not differentiable. So you can't use any of the other things you know from behind. There's first derivative exists, I can do this. Second derivative exists, I can do that. Not even doesn't even, derivative doesn't exist. Max is not differentiable. But some beautiful geometric things will give you that. So this is convex just by the fact P of this is convex, intersection is convex, so this is convex, so G is convex. Okay. I also asked you last time about this composition, FOG. Is this convex? So all you are given is F and G are convex. You can work with examples. Just give me an example where it works and give me an example where it doesn't work. Possibly. What about, let's say G be 1 by x and F be e to the power x. Legit functions, right? 1 by x is convex, e power x is also convex. So what will this look like? E to the power 1 by x. Is that convex? It's too nasty a function to think about. What kind of function is, first of all? Increasing, decreasing? E to the power 1 by x. Yeah, decreasing. How is it decreasing is the question. It's too nasty, maybe. Think of something simpler. Replace f with, let's say, e to the minus x. Then what happens? You get e to the power minus 1 by x. What kind of function is that? Advantage is that e power x as well as e power minus x, both are convex. That is very rare.
That's not.
What does it look
About
like?
something like that. Like towards zero effort is zero and it goes to one.
So g is, let's say, 1 by x, and f is e to the minus x. So what is f of g look like? The minus 1 by x. What is that 0, first of all?
Yeah, so
E to the minus infinity. So it's 0. Okay. So it's 0. At x equal to infinity, this is 1. E to the minus, yeah, so it's 1 somewhere. Okay. And now what do you want? You're saying is something like this?
yeah, because otherwise like it has to approach one, right? If it goes
It does. So it can't be from below. It's increasing at least towards the end. And if it does, then it will cross. It won't be like something like this. That would be very, even that also would be, if that also happens, you're okay. Doesn't necessarily have to start bending here. Even if it eventually does that, initially it is this, it's not good. So it's not necessarily true that FOG is convex. What extra condition do I need to make it work? Convexity is, like, let's say, required. What more do I need? Just convexity alone is not sufficient. If you notice something from the example, you'll catch it. What kind of functions are f and g? They're both decreasing. I intentionally created them. So can you just fix one of them and say, now it's okay? Which one do you insist should be non-decreasing? Both decreasing is not working. So the simplest thing I should take away is at least one of them. So which one of them, if I make it non-decreasing, do you think I'll make it work? G.
because
Uh-huh.
the domain of f will be non-decreasing, and since f is convex.
Yeah. See, the eventual operator is f. The first operator is g, but the eventual operator is f. Just notice something. That's all. Which among the two is more important? You ask for both increasing, that's too much.
G, right? I mean, G increasing.
Mhm.
Then we can kind of put into a one-to-one correspondence with R itself. And then F is going to be doing it on something that looks like R. So,
Let's see, let's try to do this carefully. Okay. So FOG of lambda x. Okay. What is this equal to? F of G of lambda x plus 1 minus lambda x. Okay, so now what do I know? G is convex. Right? So again, internally I could write something less than equal to. But if I want to move that here, what do I need? F is not decreasing.
okay.
See, this part, I have an inequality of this type because G is convex.
Yes.
But I can't move this here unless I have something on F. At this point, I don't need the convexity of F. All I need is that it's not decreasing. Is this clear?
Yeah.
Okay, let me write it as, see, this is the problem. I can't write equality here. So I have to jump 2 steps in one go. So I want to write the following. F of lambda G of x plus 1 minus lambda G of y. Why is this true is the question. F is non-decreasing. How do I get it? Internally, because of the convexity, this is larger, this is smaller than this quantity. I'm not keeping it here because that makes no sense. I'm moving it to the outside, and that is only allowed if F is in fact not decreasing. Now it's like essentially lambda times FOG of x plus 1 minus lambda times FOG of. No? Which one? This one. Why?
So we are bringing lambda outside.
Okay. So
That will equal to itself. Because it will take operating f of the function. And so that it will just be equal to that. So then we're splitting the argument of that, right? I know, like f of a plus, let's say f of x plus g. It will just be f of x plus f of g. That is only perfectly.
F is only given to be convex.
Oh, okay, it's not really.
Everybody happy with this? What happened? No.
Like
Here to here is okay.
less than it's-
Okay. So why is this true or not true? F is convex. So treat g of x as a new point, g of y as another point. So what are we taking? A linear combination of lambda of gx and 1 minus lambda of gy. So now f goes in with a less than equal to sign because of convexity of x. So until this point, I didn't use f's convex. So this is true irrespective of f is convex or not. This is true because don't lose the sight of it. This is the domain of G, while this is the domain of F. Right? That's what FOG means. That G's domain is essentially X, F's domain is essentially range of G. So whatever examples you're creating, the outer function, the function which is getting operated the second, that needs to be non-decreasing. As long as that is true, you get that the composition is convex. So that's why the example we created, the outside function was not decreasing, e to the minus x. That did not work, and that is why it didn't work. So if you take any function from the outside, which is e power x or whatever, it doesn't matter what g is. G is, as long as it's convex, decreasing, non-decreasing doesn't really matter. It'll be fine. So don't lose sight of every single property we have. Everything is needed. Because otherwise F's convexity was not important. It's important. Okay. Let's stop here. Next time we'll prove. What will we prove? You can try to claim it yourself. That would be an interesting homework. Like, it's not part of homework, but good to at least absorb that what is an epigraph is. This definition is very important. That you should carry on the class. From 2 years from now, if somebody does something, you're reading a paper, he does something with epigraph, you should be comfortable. So what is epigraph? And the proof or the theorem we're going to prove that a function is convex if and only if its epigraph is convex. We'll prove that in class as well as if it's appealing, try to do it yourself. Don't look in the book, just try to do it yourself. And then we'll go to the differentiable convex function. If it is differentiable, can I give an alternate description of a convex function? If it is twice differentiable, what is an alternate characterization of a convex function? See, here the advantage is I don't need differentiability. So when I'm being asked a question, is this function convex? I can give you an answer without knowing its differentiability. More generally, differentiability is very useful because we'll also try to give examples where it's very easy to check if they're convex or not, just by looking at the sufficient, necessary and sufficient conditions coming from the differentiability of it. This will not be potentially useful. Give one example where it's very easy to check if a function is convex if I knew something about the derivatives.
Second derivative is trivial.
For example, 1 by x, just trivial to check. But otherwise, it makes it job is quite hard. We looked at it. So these are all equivalent descriptions. We just make our life simple. Okay, let's stop here.